question 18 begins simply with a definition of Kc for this reaction. So Kc, remember, is in terms of concentrations, and the stuff on the right goes on the top. So we have NO2 squared, and then the stuff on the left goes on the bottom, so NO squared, because there's two of them, times O2. So that's our expression. And then it wants the units. So just like with rate constants, it's worth learning a recipe for the units, because it's quick and it's safer than just sort of figuring it out. So the recipe for this one is that if we set x to be powers on the top minus powers on the bottom, then the units are moles to the x dm to the minus 3x. Okay, so that's very easy. So in this case we've got 2 on the top, 2 plus 1 is 3 on the bottom, so 2 minus 3 is minus 1. So it's going to be moles to the minus 1. dm to the minus 1 times minus 3 is plus 3. So moles to the minus 1 dm cubed. So then we have to use this information. So this is moles to the minus 1 dm cubed. We now know we have to use this information, which was in the question, to figure out the amount in moles of NO2 in the equilibrium mixture. So the first thing is to recognise that we've got to turn these moles into concentrations. So let's do that. So we get that the NO concentration is moles over volume, which is 0.40, and the volume, it tells us, is 4.0 dm cubed, so it's 0.4 over 4.0, which is 0.10 moles per dm cubed. And likewise the O2 again is moles over volume, and this time we've got 0.8 moles of oxygen, so 0.8 over 4.0 is 0.2 moles per dm cubed. Okay, so we've got the concentrations. The next job is going to be to rearrange this expression to solve for the NO2 concentration. And that's easily done because we've just got to shift these two numbers, which we know, over to that side. So sliding diagonally across, we get that Kc times NO squared times O2 is equal to NO2 squared. Which is, so Kc is 45, so 45 times 0.10 squared times 0.20 will give us our NO squared. So we've got 45 times 0.01 times 0.2 is equal to 0.09. Moles squared dm to the minus 6, and therefore NO2 is the square root of that, because that's NO2 squared, so that's going to be the square root of 0.090, which is 0.30 moles per dm cubed. Is the answer. Except it's not the answer, because it asks for the moles. You've got to watch out for that. I nearly fell into the trap there. That's almost the answer, but it wanted to know the moles. That's the concentration. So the last step, just carrying on over here, is that moles of NO2 is concentration times volume, which is 0.30, and the volume is still the same, of course, is 4 dm cubed, so 0.30 times 4.0 is 1.2 moles of NO2 is the actual answer to the question. Okay, so part C now is shifting to KP, and KP, remember, is again the stuff on the right goes on top. It doesn't ask you to define this, but it may just be worth scribbling it down just to make sure you remember what's going on. So it's the partial pressure of NO2 squared divided by the partial pressure of NO squared times the partial pressure of O2. So that's the function that we're talking about. And it tells us that when we go to higher temperature, so when we go from 298 to 1000, the value gets smaller. Okay, so it's going from 10 to the 12 to 10 to the minus 1. Okay, so we can write down that Kp decreases at high temperature. And of course, if the value of this decreases, it means that the top line decreases. And if the top line decreases, it means there's less NO2. And if there's less NO2, it means it's shifted backwards. Okay, so we can deduce from that that if the top line decreases, it's shifted backwards at high temperature. And now we bring Le Chatelier into play, because he will tell you how it will respond to a temperature change. And remember, he says that whatever you do to the conditions, it will try to do the opposite to oppose the change. So if you increase the temperature, it will shift in the endothermic direction to take heat away and try to oppose the temperature increase. So combining that with this, we know it will shift in the endothermic direction. So shifts in the endothermic direction to oppose the temperature increase. So putting those two things together, it shifted in the endothermic direction, it shifted backwards, so fairly obviously backwards is endothermic. And therefore the forward reaction is exothermic. And that's the answer to the question. Part 2 wants us to say what's going to happen to the position of equilibrium if we increase the pressure. If that's all it said, we could just wheel out Le Chatelier and say, right, if you increase the pressure, it will shift in the direction where there are fewer moles of gas, which is to the right, so we know that's the answer. But that's going to get you no marks. And this is where you've got to be very careful with the wording of the question. It says explain in terms of Kp, and when it says that, that means you can't use Le Chatelier. So make sure you read the question carefully. 'Tis though worth just remembering from Le Chatelier that it will shift to the right, because that's the answer we've got to get, but we've got to get it using Kp. So the first thing to remember is that the only thing that changes Kp is the temperature, and we haven't changed the temperature, it says at the same temperature. So we can write that down to start with, that Kp is unchanged, because it's the same temperature. So then we think, right, well, what's going to happen if we increase the pressure? And you can see it's going to increase the pressure of all of the substances because they're all being squashed down. But that's going to affect the bottom line more than it will the top line, because we've got pressure cubed on the bottom line. Remember, this was our Kp expression. Okay, so it's partial pressure of NO2 squared divided by partial pressure of NO squared times the partial pressure of O2. So if all of these increase, the top line is going to increase as a function of pressure squared, but the bottom line will increase more because it's pressure cubed. So we can write down that the bottom line increases more than the top line when the pressure increases, because it has a higher power of pressure. So what does that mean? Well, if the bottom line increases more than the top line, it means the value of that expression will get smaller, because we're dividing now by a bigger number. So that means that the value of the expression gets smaller. Now you've got to be careful though, it's not the value of kp that's getting smaller, because as we've just said, kp is unchanged, but the expression that should equal kp it gets smaller. So the value of the expression gets smaller. And to return to equilibrium, we've got to bring it back to kp, that's the point. So it's therefore got to get bigger again. Okay, so to return to kp, the value needs to increase. And how does it increase? Well, it increases by making the top line bigger, which means it has to shift in the forward direction. Okay, so shift in the forward direction. Is going to be the answer to the question, but just to spell it out, to make the top line bigger. Okay, so we've come to the same conclusion as Le Chatelier did, that it shifts to the right in the forward direction, but we've done that without using Le Chatelier's principle, and that's what it wanted you to do. So you've got to read these equilibrium questions carefully, and this kind of explanation, you know, it's a bit convoluted, so you need to practice those a little bit, because they come up quite often, and once you've practiced them they're easy, but trying to make it up if you haven't rehearsed it in advance is quite challenging.